So this is the agenda, and I'll try and work through it fairly steadily. We talk a little bit about his early work and the influence of Max Noether and Macaulay's visit to the International Congress of Mathematicians in 1904. Noether had a big theorem which governs the theory of plane curves. When you go into higher dimensions, the theorem breaks down. I'll discuss that a little. And what comes along to advance the situation is a famous theorem, mathematics, Lasker's primary decomposition theorem for polynomial rings. There's then a gap in Macaulay's career until 1913, when he writes a paper for Mathematische Annalen and introduces the concept of perfect ideals. If it's in red, I'm going to attempt to explain what the concept means at some convenient moment. He then publishes a Cambridge Tract in mathematics. We refer to that as the Tract, 1916. More terms for me to define as and when. And he writes two more papers of relevance to this talk, and then I'll finish up with some remarks about his legacy and his posthumous reputation. This is the only known photograph of him, a rather forbidding figure, I think. It comes from the school where he taught, St. Paul's School in London. I don't think you would want to tell him that the dog ate your homework exactly. And this is a person who has a great deal of influence, beneficial influence to him in the early years, Charlotte Angus Scott, who was unofficially ranked between 7th and 8th students at Cambridge in 1880. Women couldn't get a degree then, not until 1945. But she was very much welcomed by the fellow undergraduates. And she then went to Bryn Mawr, a founding member of the faculty of Bryn Mawr, and there she had a very distinguished career in American mathematics. Okay, Macaulay himself. He goes to Cambridge, he graduates 8th Wrangler, means 8th in list of order of merit, 1882. He joins this society in 1886, which is a sign that he intends to conduct research. He writes a string of papers in these early years aiming to make the theory of Max Noether more precise. Actively supported by Charlotte Angus Scott, who reviews his papers, gives them advice. And the best result, the only one I'll try and discuss at all in these papers, is what he called a one-set point. Okay, that's a novel concept with Macaulay that I'll get around to trying to motivate for you. This is Max Noether. People in the day would circulate photographs of each other because you weren't going to travel much and meet. So if you wanted to know who this Max Noether person was, you might get a photograph like this. And van der Waalen, who knows whereof he spoke, said algebraic geometry was created by Max Noether. He immediately added, although the logic of some of his arguments was not secure. Okay, but nonetheless, that's Max Noether's thing. Now, what's the big deal here at this time? The big deal is a theorem largely due to Riemann, completed by Roch, associate of his really, which tells you about the existence of meromorphic functions on what we would call a Riemann surface. Okay, this is the simplest I can make it, and it's vague, not altogether precise. Imagine you have a Riemann surface. Think of it as just a surface defined by a polynomial function in Z and W, and you specify a certain number of points, and you ask, are there functions which have poles at those points, but certainly nowhere else, right? And Riemann had an inequality telling you the dimension of that space. Roch interprets that inequality as an equality by explaining what the difference is. It has to do with the space of holomorphic one forms, the things you integrate on that surface. And the result is that this minus that.
Sorry to interrupt. Yeah. Sorry, do people on Zoom aren't able to see your presentation because Adobe doesn't, PDFs aren't able to be presented. So I've just converted your presentation to a PowerPoint. Would you mind just give me a couple of minutes just to switch over? So people watching.
No, that's fine. That's fine.
Sorry about this.
We should have done it before.
It's great we have such an online audience.
It is. Yes, I hope they enjoy it. I should say, if anybody wants a copy of this stuff, they email me. I can send them at least the talk. Yeah, they were shot by one. Can you go back one?
I think you shared the PowerPoint, not the PowerPoint view.
Sorry, say that again.
You shared the PowerPoint, but not the view presentation, so you stop sharing. Then share again.
Sorry, did you say that again? Oh, yeah, come up here.
So you shared this, that's it, you want to share this one, slide share, so.
I think that's what. Is this the correct slide you were?
Yeah, well, the next one, we'll go back one. Okay, so takeaway message from this is you want to know of a surface, thought of as an algebraic curve in two complex variables defined by a polynomial. Are there meromorphic functions on it? So they have some poles somewhere and not too many poles, but only a specified number. You discover that there's a connection between the dimension of the space of these functions and the space of one forms, which don't behave badly except possibly at the same collection of points. And the difference of these two dimensions is given by the number d of points you're talking about, plus 1 minus g, a number which is the genus of the curve, and in Riemann's mind is something you get by cutting it up, by drawing loops on it and closed curves on it, and proceeding until you cut it into at least 2 bits. That's the number of, will eventually define the genus. Oops. And this is a fact been known before Riemann by people like Abel. This rather forbidding expression is how you write down an everywhere holomorphic integrand on one of these curves. If you take f to be a quartic and do the algebra, you'll discover you can get away with phi being of dimension 1, and it looks like an elliptic integral. Okay, so that's the you can then count constants and work out the dimension of the one forms on a curve like that, if you're lucky, right? Okay. Max Noether, Alexander Brill attempt, inspired by their predecessor, Rudolf Klebsch, is to say, look, Riemann stuff is terribly complicated. People aren't convinced that his foundations in potential theory make any sense. They're not sufficiently rigorous. So we're going to interpret a function of f and zw as a function in the plane complex numbers, right? So we've now got a plane algebraic curve, a complex curve, and everything has to be translated from what I said before to their language. So, for example, you can determine how many constants there are on a curve you're talking about in terms of the degree. You can get a formula for the genus, which involves a certain number of double points on the curve where it crosses itself, and a certain number of points where it has a cusp. What's a cusp? Something like that. I think y squared equals x cubed here. There's numbers invariant and a rather large class of what are called birational transformations. But look, if you are interested in no singular points at all, so delta is 0 and rho is 0, then this number is a triangular number, right? So, for example, there are no curves of genus 2 which do not have singular points in the plane. Okay, the ones that do not have singular points in the plane are 0, 1, 3, 6, 10, and so on. All the other ones are going to have singular points. Singular points are inescapable in this theory. Okay. Yeah. Seems like I want to move on. Ah, okay, good. Okay, so now you have to think about how Brill and Noether went about defining points of interest. And what they said was, look, you've got the curve you're interested in. I may occasionally call it the ground curve, like they did. Specify points on it. You take another curve which goes through those 3 points, the points you want. Okay. Maybe you want to specify 7 points. Fine. You pick a curve which goes through those 7 points. Okay, because it will go through some other points on the curve by and large, it has to satisfy Bazou's theorem. Statements about points, statements about families of curves through those points, statements about one forms doing something at those points, all have to be translated into statements about curves of certain kinds going through those points. Well, Riemann had points, Brill have curves. And those curves are intersecting the curve you're really interested in, the ground curve, which I've called gamma here. Okay. These curves you're interested in, along with the curve you're really talking about, the auxiliary curve, may also have singular points. They may have very bad singular points. They may cross each other at the singular points. Right? You've no idea what they might do, but the extent of the intersections have to be counted, right, in order to get these dimension counts to work. The fundamental theorem here is due to Max Noether from 1872. You have 2 plane algebraic curves. I've given them in their projective coordinates this time. So you know intersection points that run off to infinity and hide. And you want a third curve to pass through these other ones so that H is expressible in this form, AF plus BG. So everything inside H, A, F, B, and G are polynomials in 3 variables. Okay, homogeneous polynomials in 3 variables. And obviously, if H is expressible in this fashion, that the points where F and G meet, where F vanishes and G vanishes, H had better vanish. So it's clear that H as a curve, H equals 0 as a curve, must pass through the common points of F and G. But that's not enough. Here's an example. You've got 2 red curves. F is the parabola, G is the horizontal line. The black curve certainly passes through the common point, but is not expressible in this form, as you can readily calculate, because you can't get x out of those 2 expressions, y and yz minus x squared. Why not? Because it only passes, as you might say, once through the point O, and the curves, 2 red curves, the horizontal line and the parabola, meet twice there. The red curve has a tangent at that point, which is what the red line is. So somehow how the curves meet is also part of the story. Okay, so Noether's fundamental theorem says if you want to express H in this form, then you have to go to each intersection point of the curves F equals 0 and G equals 0 and do a check. And that check says, can you find, well, power series is languages that are clumsy here. Can you find power series, which are, of course, locally defined things? At each singular point, you get different power series each time. You go to, let's say, this singular point here. Can you go there and find power series A prime and B prime, such that that equation there for H is satisfied by A prime F plus B prime G to a sufficiently high degree? How high? Another question. But that's the test. It's a thing really to remember from this is it's a local test at each point. This theorem says that if you want to know if H can be expressed in the form AF plus BG, you go to the intersection points of the curves defined by F and G, and you run a test. If it passes this at each test, then it can be written like that. Okay. On the basis of this, they established what's called, well, they were the first to call, actually, the Riemann-Roch theorem. And what to do about singularities? It's not enough to say you've got taken care of the double points and the cusps. That's very, very easy. The singularities may be really quite awful. So what they said was, well, look, you can reduce the singularities to a collection of double points and then we're done. And this argument is rather sketchy, shall we say, in the hands of all of these people, but it was generally believed. And there's no sort of real feeling it was wrong as a theorem, but there was some laxity about whether you'd established it. Okay. What do we know now? This is a statement a little inexact, the way I put it. If the curves F and G meet transversely, they cross each other nicely. Separate, all the tangent directions in question are different. Then it's true. You can make this work by counting constants. Okay? And you can do it all by having some set theoretic argument about what are points on the curve. And that's the only case. You might be able to work out some other things, like the example of the parabola and the line, and you say, oh, I've got some multiple intersection here, but it's a double point somehow. Okay, but in general, it gets too complicated. This is where Macaulay began. He wanted a geometrical theorem in terms of these complicated things. Okay, and we now know it won't work. Okay. Oh, well, I knew when it got converted from Beamer to PowerPoint that something would die. The missing symbol, you might guess, if I could get it on the screen, there we go, is the summation sign, of course. All right. So you're going to ask whether H, with some expression.
You can write it on the board.
No, okay, if you want to write
Let's
it,
go
that'd be fine.
old-fashioned.
Yeah, sure. But I think
Here's a piece of chalk.
I think I'm going to have a summation convention. Right. Okay. Here.
Yeah.
Okay. H is the sum over I and J. I don't know what X is doing there. X is probably a mistake. So it's probably a good thing I'm writing it. A I J X to the I, Y to the J. Okay. And I want to know if it belongs in the ideal defined by X squared. Oops. X squared. Oh, can I clean this off? That's good. I might do it tight that. Much better. Thank you. X squared and Y cubed. Okay. So H comes to us as some kind of polynomial in powers of X and Y multiplied together, maybe. Okay, these are the appropriate coefficient. And I want to know if that's true. Okay. So you just write down the necessary equations and you discover that all the lower terms, right, you're not going to get an X, you're not going to get a Y squared, you're not going to get an XY. Okay, so these various things, there's no constant term, there's no A0, 0, and so on, right? You get these equations for it. And these are the necessary and sufficient conditions in this case. And Macaulay called them modular equations. This is language that goes back via Kronecker to Gauss, okay? And these are the necessary and sufficient equations for H to be of that form. Okay, good. Now, this is what the first thing Macaulay notices that people had missed. If Y squared is in the ideal, then of course XY squared is in the ideal. That is the definition of an ideal. So, contrapositive, if XY squared is not in the ideal, Y squared can't be. In terms of the coefficients, if A12 equals 0, then A02 must be 0, and all of these, in fact, vanish. So all of the equations you saw before are consequences of A12 equals 0. Okay, it's just a bit of algebra, really. Macaulay called them derivates of it. And this is a one-set point. All the algebraic conditions required for H to be of that form are consequences of one equation. That point, that's the only intersection point of X squared and Y cubed, of course. So at that point, you do the check. All the conditions you need check on Noether's theorem are consequences of one thing. It's a one set point for that reason. There are two set points and three set points, but not in this talk. Okay, here's a bit of Macaulay in his own words. It's not terribly digestible, but I'll try. A base point is a point that supplies conditions for a curve. Algebraic conditions. You've met a base point just now. It specified that A12 was 0 and A02 was 0 and so on. It has a degree equal to the number of independent equations to the point, which is the number you get if you pull that point apart and say, oh, look, I've got actually 7 intersections here. Try moving your curves a little. And then golly, isn't it complicated? The degree of the whole base point common to two curves is the same as the degree of the intersection at that point. A given one set point, is the complete intersection of two fixed curves at that point, and conversely. Whole base point common to two curves at that point is a one set point. So a whole intersection, a complete intersection, is a one set point, and vice versa. It's complicated the way he says it, but that's basically the insight here, that a one set point is like a complete intersection. So now I want to take you back momentarily to the ground curve we're interested in, gamma, and we said to do plain algebraic geometry on this thing, we have to intersect it with other curves. We'll take a curve, we'll call it C1. It meets gamma in some points. Some of the ones you want we'll call R, and then there's the other intersection points, which we'll call Q. They're called residual sets because between them they make up the intersection of gamma and C1. Okay, now you take another curve, C2. It goes through Q1, but obviously some other points which I'll call R2. So I now have two R's and one Q, and the sets R1 and R2 are called co-residual because they have the same residue Q1. And now you prove that if points are co-residual, they're co-residual with respect to any residue Q. So you can forget about Q, it just has to do with being co-residual as an equivalence relation. Okay, now Macaulay was the first to realize that these intersection points, these residual points, might, for example, overlap. They might be at the same point. Any kind of thing can happen. And it's only on the ground curve that a one set point can be divided into more than two base points. You can separate out the algebraic conditions into two bits. And only on one set point that this division can be done at all, that you can do the counting at all, so far as has been shown. And this is what gets to be called double residuation later on. It's essential for proving the Riemann-Roch theorem because that's a counting theorem. You have to know what you're counting, and this is the first time someone's been able to do it properly. And it means that for a one set point, you can divide it into 2 points and say that the number here, the total number can be divided into this lot and that lot, and the number here, that the total number minus that lot is equal to that lot. You can count, you can subtract. Okay, absolutely crucial to everything that was to follow. Okay, on the basis of this rather impressive piece of work, Macaulay, who by now a school teacher at St. Paul's, right, is invited to the International Congress in Heidelberg, doubtless by Max Noether, who was one of the organizers, and gives a paper generalizing this to higher dimensions. Some of his conjectures, I would say, not his actual claims or proofs, some of his hopes for how it will go, are wrong. And Max Noether takes him aside and says, have you read this book? You really should. It's a snappy little 600-page outfit in German. Really saying, look, Kronecker explained algebraic geometry, but you know, Kronecker, very unreadable. I'll go have a go. So Koenig has a 600-page go, in which, among other things, he extends Noether's fundamental theorem to things which are defined by n functions in n variables. Okay. Noether's fundamental theorem is going to fail in higher dimensions, and here's the simplest example. You're going to look at this curve. Well, you will, if I can point my finger. There we are. Yes, s to the fourth, s cubed t, no s squared t squared term, st cubed t to the fourth. The ideal it defines actually is this. It's cut out by one quadratic curve, one quadratic surface, sorry, and three cubic ones. Okay, let's call the quadratic one Q1 with the quadratic equation you see here, right? And three cubic hypersurfaces. All right. Now we're going to cut it with a plane, conveniently in those four rather nice points. And we're going to get ourselves an ideal which makes the arithmetic simple. So we have the ideal of 4 points. It's the ideal defined by the thing that defines the curve and this extra plane that comes in and cuts it. If Noether's theorem were true, you've now got 4 points. And the claim is that anything that passes through these points must be a sum of the plane, sorry, the quadratic, and the plane. four family parameters, which will be of that form there, right? Lambda h, where h is your hyperplane, and q1. Its other quadrics will be of that form. Well, dimension count says there's some that aren't, and elementary algebra says here's an example of one that isn't. There are things which are not of that form, okay, but pass through these points. So the idea of testing at each point is insufficient. It doesn't tell you enough. Let's press on. I leave ahead to give you an example of explanation of really what goes on. This is the primary decomposition of the ideal of those 4 points. So the I is the ideal defined by the curve, and y instead is the ideal of the plane. First 4 primary ideals are the first 4 points, right? And then you have this extra ideal sitting around. The failure of the fundamental theorem means an extra ideal has turned up. It's not related to the 4 points. It's another test. Testing at 4 points alone is not going to be enough. And we'll come back to this. But notice fundamental theorem fails, okay, at this point. Right. All right. A little bit about Macaulay. I said he was a school teacher at St. Paul's. He'd been there since 2 years after graduating from Cambridge. Outstanding run of success, by the way. So 4 pupils were senior wranglers at Cambridge. There were 6 Smith's Prize winners, 2 fellows of the Royal Society, Littlewood and G.N. Watson, students in successive years. The way he ran it was, he sat at his desk. The lower 6th and upper 6th pupils were in the same room. And he would write problems on the board or have handed them out. The challenge was for the junior people to do them. If they couldn't, they were allowed to ask the senior people. If the senior people couldn't do them, they were allowed to ask Macaulay, and he had to do them on site. Okay? And the honor, according to Littlewood, who wrote about this, was quite a big deal to get up and do one of these problems. It's quite a competitive environment. It's also part of a system at this time of the more ambitious schools in England to get people into Cambridge in the second year. Cut out the first year and go straight in to the second year. Okay, the head of department resigned. Macaulay assumes, on the back of all of his strength, that the job will come to him. It doesn't. And he's so enraged that he resigns after some negotiation about his salary. It's impossible to say what £170 a year is, really. You try various ways of looking at it. Roughly speaking, lower end, 69,000 present money, upper end, just over 109,000 present money, depending on what way you calculate this. Here we come to Lasker, world chess champion at the time, over in New York. The whole story is that somebody finally discovered the biography of the bit of Lasker where he's a mathematician. You try finding biographies of Lasker, you get the chess world, right? It's sort of biographies sort of go, born here, did maths, first international recognition as the grandmaster, pages and pages. Okay, he publishes this article in Mathematische Annalen for volume 60, in which he uses the concept of modules and ideals. David and I ruthlessly turned everything into ideals because that's what they are mathematically. This is the residual ideal of n with respect to n, the things you can multiply n by to get it into m. And if you need to remind yourself of that, the things you multiply anything that's a multiple of 2 by to make it a multiple of 6 are obviously any multiple of 3. Okay, so that's the way to remember it. And this is a novel concept of Lasker. And he also introduced the concept of a primary ideal. Now we think of a primary ideal down at the bottom, right? If 2 points belong to a product belongs to an ideal, and you know for sure that one of them doesn't, then a power of the other one does. Primary ideal, you would say if 2 of them belong to the product rather belongs to the ideal, and you know for sure that one of them doesn't, then you know that the other one does. This is a power of it. Why would you want that? Well, think the factorization of integers, right? You might want to factorize, I don't know, 6. It's, 2 squared times 3 squared. You need powers to do it, right? So the definition here proceeds by talking about the varieties defined by these things, the things in space defined by. The fact it's equivalent to ours is via the Nash-Sheldon-Satz, which tells you stuff like that. So the definition is a little bit convoluted because at this stage you're dealing with polynomial rings, and people like to talk about the varieties, the point sets in space, whatever dimension, corresponding to those equations of finding the ideal, but actually it's strictly equivalent. And Noether's theorem says you can take an ideal in a polynomial ring, and you can represent it as an intersection of a bunch of primary ideals. And this process proceeds by taking the biggest ones and then smaller ones and then smaller ones in terms of variety, until you get to an ideal at the end, which contains no points. Or the whole process stops before for some reason, which it will for nice ideals. Okay? So this is rather a disturbing thing. You have an ideal that belongs to the primary decomposition, but it has an empty variety. And you met one, actually, when we did the failure of Noether's fundamental theorem. That R is actually empty. There's no points corresponding to it. Okay, right. One way of defining an ideal and talking about variety is this. You pick your dimension of your space, let's say n variables, and you pick a polynomial in those variables. Now you ask about the zeros of that polynomial, you have a variety. And then you do it again. And now presumably your variety, which is the intersection of those two, the points common to the common zeros of both of those functions, is a bit small. And you carry on doing this. And if what happens is each time you chuck in a new function, the dimension goes down by 1, then you what's called a regular sequence. It's the algebraic generalization of a complete intersection. It needn't happen. Okay, but it does in the case of plane curves with no branch points, with no branches in common. And by the way, Koenig's generalization of Noether's fundamental theorem is precisely to things defined by a regular sequence. Okay, so that's a very special case, very nice kind of ideal. Lasker's theorem is the first one, is the primary decomposition. Here's where we can put it to work for a regular sequence. It says that the ideals correspond to the varieties that make up the intersection. So just you have an ideal consisting of those H functions, you're going to get some corresponding varieties which are irreducible. You're going to be talking about those things and their intersections, and that's all. So you're going to get just those ideals, okay, in the regular sequence case. Now, a little bit of language will kind of help you. Again, if I've got an intersection, an ideal written as an intersection of things, you can ask, well, can I drop one of these ideals in the intersection out? Is it already redundant? Is it contained in the intersection of the others? If it isn't, then it's said to be isolated, and what you have here is that there are points on its variety, its zero set, which are part of the whole thing and are not defined by points anywhere else. The relevant primary ideals are the ones that are not droppable. You can't throw them out. Yeah, we've got all the intersection. Okay, and that's what you work with. Lasker doesn't show that when you're dealing with regular sequences, you get primary components, all of the maximal dimension first. Macaulay does, that's one of the things, improvements he makes. Okay, so to sum up, two curves in the plane, the case that Noether dealt with mostly, that Macaulay was more rigorous about, that is covered by Lasker's theorem, and the result is you have one primary ideal for each intersection point of the two curves. That means you can test for membership of that ideal by going to each common point in turn and checking there. Mind you, that mightn't be easy. Macaulay explicitly says he has an eye for what you can actually do computationally. It might be no easier than testing for membership, but the primary decomposition says that it's a local test, check at each point, in the case of plane curves. For higher dimensions, when you do this process of finding the primary decomposition, you may be left with, for example, an empty variety. No membership test applies, but it is an essential member of the primary decomposition. Okay, so Macaulay has retired from Cambridge on his new salary, from St. Paul, sorry, on his new salary. He goes to Cambridge eventually, not immediately, but eventually. And he writes a paper in 1913 which he wants to send to Madame Marshall anonymous. It contains these interesting things and others. The concept of residuation is one of them. Something called a perfect ideal, which he introduces, and I'll try to explain. And some connection between his earlier work and work of Hilbert, and what are called Hilbert numbers and the Hilbert function. It also has this stuff. If it puts something on the blackboard, on the screen, which is in brackets, I'm not going to talk about it. I just want you to notice that I've had to chuck stuff out of the lifeboat, sorry about that, in order to get talk to manageable size. Okay, plenty of other stuff done by Macaulay, in other words. That's all I'm saying. Okay, perfect ideals. Let me sell you, as Macaulay did. Perfect ideals before I tell you really what they are. The varieties associated to the primary ideal and the primary decomposition of a perfect are all of the same dimension. No smaller varieties lurking about, no plane meets a line, or plane has a line sticking out, that kind of thing. Okay. Perfect ideals are what are called unmixed. A term he actually introduces 3 years later. Sorry about that. And unmixed ideals turn out to be precisely the ideal of which Noether's fundamental theorem generalizes. Although Macaulay didn't precisely say so, but perfect ideals are unmixed ideals are precisely the ideals that allow you to generalize Noether's fundamental theorem. So if you have a setup and you want to know if Noether's theorem applies and all the membership tests are local, your testing is unmixed. Okay. These modular equations, all right, in any given setting, there's a maximum number of things that could arise. They don't necessarily generate the maximum number of modular equations in any given setting. Ideals which do that are what he called perfect. Okay, so you have a very close connection to the maximum number of modular equations that are needed when you're dealing with an ideal. Okay, I won't say much more about it because it's quite technical. Okay, perfect ideals have this lovely property. If you have an ideal M and it's perfect, and it's sitting inside an ideal M prime, you form its residue. M double prime is the residue of M prime with respect to M. And now you take M double prime and you look at the residue of it with respect to M, and you get M prime back. So you can flip from M prime to M double prime and back. That's double residuation. It's rather like thinking about you have a residue here, the other bit, and a co-residue. Can you flip backwards and forwards like that? It's a generalization of that. Okay. This is not something that was picked up by Emmy Noether. Emmy Noether picked up a lot when she writes a paper in 1920 on primary ideal decomposition, the Ringbereich paper that makes commutative algebra modern. It gets discovered actually in 1974 by Peskin and Spiro. It's called Linkage, Liaison of Cohen-Macaulay Ideals. Okay. Well, Macaulay's written this paper. He wants to go to mathematical analysis. He writes this very defensive, apologetic letter to Hilbert saying, well, I've done this, and I would like it to go to analysis, but if you don't want it, just let me know, and I can probably get into one of the London journals. But could you do so quickly, please? Because, you know, I'd like to be finished with it. I've held it back for a bit because I think it's true that prime ideals were perfect. We don't have Hilbert's reply. We have very little correspondence kept by Macaulay, none. And so Macaulay carries on working, and at some stage when the paper's finished and been submitted, he realizes this example we met before is also an example of a prime ideal that's not perfect. And this is a sketch of the proof modulo a condition I haven't been able to define for you in time, which is at the bottom of the screen there. This one here. So at all events, he realized that the letter he'd written to Hilbert saying, I'd like to prove this. Bit of a blunder, really, because it's just not true. Okay, the Tract, published in 1916, not the best year maybe for a paper or a booklet that you want to make your name. Has the concept of unmixedness, which is still around, things called determinantal ideals, which I will define, yet another definition of perfect ideals, and another proof from that definition that perfect ideals are unmixed. I should say it took David quite some time, well, an afternoon, to prove that these definitions are perfect are all the same, right? And I just stared at them, but they are apparently. And a whole bunch of other stuff, which I'm not going to be able to talk about, although I have to say, at one point it's a shame, I thought, because actually the theory of inverse systems is a theory of duality, and we have a speaker on duality next, but there we go. Okay, an unmixed ideal is very nice. All of its relevant varieties, all of the things that simplify are isolated or embedded are of the same dimension. An unmixed ideal has no relevant embedded varieties, nothing, no varieties hiding inside other ones. Okay. Primary ideal is unmixed, and its corresponding variety by an earlier theorem is reducible. Determinantal ideals, fine, just take a bunch of your favorite polynomials and put them into a R by K matrix. And look at the R by R minus, because R is less than or equal to K, and look at the ideal that that's generated by, and look at the variety that you get. What's the codimension of that variety? It must be less by simple counting than K minus R plus 1. And if it isn't that, you have a unmixed determinantal variety. If you let R be 1, this is the condition that the maximum value of the codimension, K, the number of things you've got in it. So unmixed would be you have K functions in variables, and they define an idea which is a complete intersection, right? They call it of the principal class. So again, like a regular, it behaves like a regular sequence. So unmixed ideals have nice properties in that way. Skip ahead to 1927, which I only want, paper about Hilbert function, for a very famous quote in the business. He states a theorem, uses it to prove a nice result, and in section 2 of the paper, he gets around to proving a theorem, and he says this. This proof of the theorem, which has been assumed earlier, is given only to place it on record. It is too long and complicated to provide any but the most tedious reading. I don't think people say that anymore, and actually by modern standards of tedious reading, I think it's quite short and has been shortened by experts in the field, but I thought it was worth quoting. By the way, he frequently doesn't have proofs. Macaulay frequently said, I'll take a 3x5 example. I think that's pretty general and show it. So another person, John called Lasker, came along and for his PhD thesis filled in the gaps. Okay, the next year, his achievements are recognized by members of the Royal Society as worthy of membership, and they cite various of his papers, and he becomes a member of the Royal Society. Moving ahead to 1934, by now he's aware of Emmy Noether, he's aware of Van der Waals' Moderne Algebra, and which of course, as Van der Waals always said, expounding the ideas Emmy Noether and Emmy Lartine, amongst others, on the theory now of ideals in commutative and non-commutative rings. And Macaulay quite correctly says, many theories, at first apparently diverse, and more or less independent, are combined by E. Noether in a wonderful manner as the theory of ideals of rings in general, both commutative and non-commutative. This is, of course, a huge step forward. Particularly praised the Noetherian chain condition as being a more subtle and in some ways more advantageous form of the assumption that every ideal has a finite basis. The theorem is always true for a ring. And then he started to summarize the basic features of the new theory. I think this is the first time it's summarized and set down in English. And finally, he adopted the set theoretic approach to ideals. So 6 is a sub-ideal of 3. Previously, people had it backwards because they looked at what the varieties did, okay? And then used that, the inclusion sign with respect to the varieties. Finally, Brill, I think, had said to people, look, come on, 6 is a smaller ideal than 2. And that should just write it that way. He goes back to the Noether-Lasker theorem, which is the generalization of Noether's theorem to primary ideals and unmixedness, and says there's no better example of method than Kroll's proof of Lasker's extension of Noether's fundamental theorem, which has not been published as far as I'm aware. And the method in question is that of modern Noetherian ring theory as exemplified in ardent Kroll. And we don't know how Macaulay knew this. He seems not to have known of Kroll's paper in 1928, which Kroll admits is a bit hard to find. So there must have been some correspondence, but if there was, we can't find any trace of it. He defined this thing called a principal system with an ideal, all of whose primary components are irreducible and isolated. That means they are really essential to decomposition, and found a whole bunch of principal systems. Principal systems are in some way the dual of ideals of regular systems, ideals of principal class. And there are lots of these things: prime ideals, irreducible ideals, ideals whose primary components are well behaved. And he introduces something called superperfect ideals, which we'll come to. And he gives you this theorem. I'm not so much interested in the result. I mean, it says, by the way, you have this business of double residuation. Okay, so that's the pair of equations in the middle. But again, there's somebody else who's working out. In this case, he knows Grosvenor's work. And again, we don't know really how. He must have been corresponding with these people. They must have been corresponding with him. Okay, and then he has this nice idea of a superperfect ideal generated, and this is the thing that really generalizes the idea of one set point, which is the best idea he had at the start of his career. You have this nice result about mutual reciprocity for superperfect ideals. One's perfect if the other one is. There's a nice tidy theory of perfect ideals and mixed ideals, and this nice class of superperfect ideals. And he has ideas of what works in polynomial rings in 2 dimensions that doesn't work in 3, for example. So a very clear idea. Okay, he dies in 1937, 2 days short of his 75th birthday. And there's an obituary, of course. Generous reminiscence by Littlewood of his time at school. Okay, a bibliography compiled by F.P. White, the editor of the Proceedings of the Cambridge Philosophical Society. The obituary, which is largely written, I suspect, by Baker, is, well, frankly, it's grudging. It says he didn't know the full extent of the Italian work and things, stuff like that. It seems to be plain wrong. It also omits a mention of Macaulay's obituary of Max Noether, and any mention of Macaulay's last paper, the one we just discussed, which White should surely know, because it was published in a journal he edited. I have no intention to apologize for White's behavior here. I don't know how it went the way it did, but there you go. Maybe he had it on file from way back and just bunged it in haste. I don't know. Anyway, his reputation, Macaulay's reputation in Germany, is very high because of the 1913 paper and the tract when it becomes available. It's referred to by Emmy Noether in his paper, her paper of 1921, the Ringbereich paper, the one that introduces the abstract methods. She singles Lasker and Macaulay out, experts on the theory of polynomial rings from the standpoint of elimination theory. Of course, that's precisely the theory she herself is trying to eliminate, but that's another thing. The methods she proposes eliminate all these precise algebraic calculations. She can use the primary decomposition without having to do the theory of resultants and stuff like that, which clutter up Macaulay's work a lot. And of course, she's followed in this regard by van der Waal and Kroll, and gradually their awareness of Macaulay fades away. But he's definitely regarded as an important precursor of this result, these results that inspire Emmy Noether to sort of rise above it. Thank you very much.
Thank you very much for a beautiful lecture. It was quite intriguing what you said about the letter. So Hilbert had the letter of Macaulay in his archive, whereas Macaulay didn't keep any of Hilbert's letters.
It seems like that's the case, yeah.
I see.
So Hilbert kept these letters. Macaulay actually then, after a couple of weeks really, writes to Klein and says, look, I haven't heard from Hilbert and I really like a decision. And Klein, for some strange reason, then, of course, he's in charge of the Annalen, strange reason, writes to Landau to say, look, can you sort this business from Macaulay and Hilbert out? So there's some correspondence on other matters. June, their family, some Macaulay correspondence on other matters, and there's some correspondence with Lama and people in Cambridge. But on the bit that we would love to have correspondence. No.
Very interesting. Yeah. Any other questions from the audience? Also, any online questions?
June.
Gary, I mean, I maybe I should remember this. I don't have, but I don't. When he was at St. Paul's, who was he communicating with? Was there anyone in London, or was he going to Cambridge? Do you think, to see Baker and people like that at that time?
I don't know. I have the impression that he didn't. I mean, he's a London University person in terms of his DSc. Right, if you want a higher degree, you can get one out of London for research. So he did that. I think the only person he cites in this period is, of course, Charlotte Anchor Scott. So definitely she was writing to him saying, and publishing things about his papers. One of his papers goes into the bulletin of the one of the papers, or the notices of one of the journals of the AMS. And so she replies there and says, this is really interesting. How about this improvement? And he has to say, well, thank you, but the improvement's wrong. So she's a real influence.
I mean, I think that's sort of interesting because she's in by then. She's
By then in Bryn Mawr.
Quite soon. I mean,
yeah,
not that long.
And I can't think of anybody that Macaulay would be talking to then, actually. I mean, Baker's still an astronomer, isn't he? I mean, he somehow becomes whichever professor.
He was the Landing
professor. And somehow at this stage he thinks, well, I better do some geometry, since that's the tradition in that chair. And I don't suppose he was communicating with Cayley.
Who do you think influenced him right at the start? I mean, because it's interesting, I think, the relationship with Charlotte Scott, given the
I think I don't know for sure. I honestly think that I honestly think the answer is quite possibly nobody, that he comes along, he's interested in these plane curve things, he realizes that the theory isn't that good, and he thinks, well, you know, maybe I can just beat the problems to death. I really rather like algebra, right? And I rather like geometry, and I think maybe I can sort out these difficult cases, right, that have eluded other people, maybe haven't even talked about them. And there is a famous theorem due very early on to Cayley, now called the Cayley-Bacharach theorem, which I won't attempt to describe. It's almost the same as Riemann-Roch in this context. Cayley publishes a theorem, and at some point it matters that a bunch of points are independent, and then something else will happen. So let's see if we can think how to generalize this. Other special cases, the early elementary cases, are Pascal's theorem, right? And Pappus's theorem. You have a bunch of points. It's okay, look, let's take Pascal's theorem. If you have 5 points in the plane, there's a conic through them. No big deal. If you have 6 points in a plane and a conic through them, there's a theorem, right? And that's called Pascal's theorem, right? I've got the right name. Right, you join them up in a funny kind of way, and you get a straight line. Right. So this kind of sits there as an example of small numbers. And you want to say that there's a kind of generalization of that. I have a curve and another curve, and they meet in a certain number of points. Now, in general, nothing happens. But if those points can be split into 2 groups, and too many of them lie on the first curve, like the ground curve, if too many of the intersections lie on that one, and not very many here, then these points do something special, like they might lie in a straight line. Okay, let's do that in general with curves of arbitrary degree, and let's see what happens. And Cayley had a theorem, and he gets the crucial bit towards the end, and he said, well, we should really want to be sure that these points are independent, and I can't prove that, but I see no reason why they're not. And it sits there, and Klebsch says this is the theorem that wraps up the whole of plane algebraic geometry. So it's passed, right? And then Noether has a student called Bacharach, and Bacharach comes along, maybe Noether prods him, because at some point people have got suspicious. Baccarat's PhD theorem is essentially finding what Cayley overlooked. I can see no reason why they're not independent. Well, sorry, occasionally they are. So sometimes that's fine. Cayley's right. Sometimes it's wrong. Cayley gets the response and says, I don't think you've read my theorem properly. And Zeuthen says, sorry, we have. And that's it. So that's a context also for Macaulay thinking there's something to sort out. But a person saying to him, look, Francis, why don't you do this? It looks a bit like it's kind of your glass of tea. I don't think there is such a person. We don't know of them.
Any other questions? Well, if not, thank you very much again for giving us a little bit of